Okay, in this section, we're going to still stick with the idea of linear, but talk about linear inequalities in one variable. And I apologize, I did not change this over correctly. So let's just say linear inequalities, not equations, in one variable. Sorry about that. So we're going to look at how to solve linear inequalities. Oh, I'll make a lot of typos here. Inequalities in one variable. And to do that, we're going to solve the process of finding the set of numbers that make the inequality a true statement. So just like before, solutions of inequalities, just like for equations, we say they satisfy the inequality and they give us all these true statements. So a solution here has the same exact definition as it did before. We're getting a true statement. The set of all solutions is the solution set. So we do see that with inequalities, we typically have more than one solution. We usually have a whole range of solutions here. So we are going to have more traditional solution sets where it's not just one answer, but more than one answer. And solution sets for inequalities can be represented in many forms. So the two that we're going to focus on here would be your set builder notation and graphically on a number line. There are other ways to write our solutions as well, but these are the two that we're going to focus on. So set notation is a shorthand. Your book will use the full term set builder notation, just so you know. Okay. Now, here are just a few examples with how to graph, and we're going to go through some of these together, of course, too. But what we do is we do use a closed dot when we are using a strict less than or equal to or greater than or equal to sign, and we use an open dot when we have a strict less than or greater than sign. So the dot being filled in or not distinguishes what type of inequality sign we have. So remember these two, this would be your less than or equal to, and your greater than or equal to, so less than or equal to, greater than or equal to. Here you have your strict less than, and here you have your strict greater than. Okay, so remember when you're less than or greater than, those end values are not included, right? End points not included. So that's why we use that open circle. It almost looks like a hole there, right? That's saying, hey, this end value is not included. Whereas here we use a closed circle to say that the end value is included. Okay. All right, so here's your set builder notation. A lot of times you'll see it shorthand, just kind of like this instead. But this is the more formal where you have your set notation here and that vertical line. Remember, it means such that. So this says x such that x is less than a. Here we have strict less than. I know it's a little hard to see, but we have an open circle here. And remember, we're shading in what's true. So we shade the true section. So if we want values less than, we're shading those that are smaller. Here we have less than or equal to. So you're going to have a nice closed circle there. And again, we're going to shade in the area that's smaller. Here we have a greater than. So you have an open circle here. And we're going to shade values that are greater than b. So those would be values on your right. Here we have greater than or equal to. So you got to see that closed circle, but shading to the right. Remember, on your number line, you have your positives going up to the right, and then you have your negatives going down to the left, right? So your bigger numbers are on the right, smaller numbers are on the left. So when we're going bigger, we're shading to the right, smaller, we're shading to the left. Now, you could have kind of end caps on both sides. So notice here, both of these are strict less thans. So your x value is less than b, but it's greater than a, right? Because a is less than x. So that x is sandwiched between a and b. So you have your open circles on both ends, and you're going to shade in between those two values. Here you have equality on both ends. So you're going to see closed circles. But again, x is being sandwiched in between. So it's going to look like this. You can mix your signs. So here on the A end, it's going to be a closed circle, but on the B end, it's going to be an open circle. And then the opposite here on the A end, open, and on the B end, closed. Okay, so those are the graphs that we're going to see. All right, so let's do it on our own. So this is a great point. If you want to pause the video and try it yourself first, see what you get. I do recommend trying that. So let's go ahead and write our graphs. Now, notice I'm looking at x values less than 3. So you don't need to put all the numbers here. I'm just going to put a few in. I want values that are less than 3. So I want numbers that are smaller than 3. So I'm shading this way. And because it's a less than sign, I'm going to use an open circle, right? So less than, greater than, get that open circle. Less than or equal to or greater than equal to, get that closed circle. Now, the part that we shade is the true side. So if you're not sure, double check. You can plug in a value. So 2 is shaded in. Is 2 less than 3? Yes, it is, right? 2 is less than 3. So I have the right side shaded, the correct side. All right, so -1 is my main focus here. I'm just going to put a few more of the points in. Okay. And I want a value that is greater than or equal to -1. I want to be bigger than -1, so I'm going this way. And notice that it is a greater than or equal to, so I'm going to use a closed circle on that -1. If you're not sure, check, right? So it says x is greater than or equal to -1. Let me plug in one of my values. Let me plug in 1. Is 1 greater than or equal to -1? It is. So your shaded area is the true area. And then finally here. All right, so I have to go -1. All the way to 3. And notice that x is being sandwiched in between. So I'm shading in between these two numbers. On -1, I have a strict less than, so I'm going to use an open circle. And then on 3, I have a less than or equal to, so I'm going to use a closed circle. So I'm shading right in here. Okay. Now, that's how we're going to write our answers. So what we're going to do now is actually figure out, well, how do you get the answer? So these are like our answers, and now we're graphing. So let's talk a little bit about how you actually get your results. So a linear inequality in x can be written in one of the following forms where a is not 0. So it could be ax plus b is less than 0, ax plus b is greater than 0, less than or equal to, or greater than or equal to. So it can be in these forms. And of course, this is the simplified version. You could also have parentheses or fractions or decimals or things like that too. But notice that we are still linear. So we're not talking about squares or cubes or roots or anything weird like that, just kind of, the more basic style. Now, what we do is we solve our linear inequalities the same way we solve linear equations. It's all the same rules except for one exception. And that's if we multiply or divide by a negative number, we do flip the direction of the inequality sign. And I want to show you why that happens. So for instance, let me give you a true statement to start with. 5 is less than 9, right? That's true. 5 is less than 9. Let's add to it. So if I add the number 1 to both sides, I get 6 is less than 10. And this is still true, right? Adding a number doesn't seem to change anything. If I subtract a number, let's subtract 5. So I have 5 minus 5 is less than 9 minus 5. I get 0 is less than 4. This is still true. Okay, so, and you could try different numbers here. So I encourage you to try others. Adding and subtracting doesn't change the truthness of the statement. It gets a little tricky when we multiply or divide though. So if I multiply by 2, then what happens is I get 5 times 2 is less than 9 times 2, which says that 10 is less than 18, which is still true. But if I multiply by -2, I get -10 is less than -18, and this is false, right? -10 is bigger than -18. So when we multiply with that negative sign, it changes it from a true statement to a false statement. So what we have to do is flip this direction. So we're going to flip it around to make it true again. And the same thing happens with division, right? So if I try to, maybe if I divide by 1, I get what? 5 over 1 is less than 9 over 1. So I still get 5 is less than 9. But if I divide by -1, what happens is I get -5 is less than -9, which again is false. So the reason we have to do this flip is because when we multiply or divide by a negative, it doesn't stay true anymore, right? So whenever we're solving things, we want to keep everything to be true. We don't want to change the solution. So that's the one thing we have to watch out for. If we multiply divided by a negative, we need to correct this sign and flip it back. So let's try a couple of examples here. And I'm just going to write this a little bigger. Okay. So I'm still going to kind of make my line here just to keep my two sides organized. And we're going to solve the same way. I have no parentheses here, no decimals, no fractions. I don't even really have any like terms except for the 7 and the 5. So the first thing I have to do is get the 7 to the other side. I'm going to add 7, and there's nothing wrong with adding 7. It doesn't change the truthness, right? So it doesn't affect the sign at all. And I just get 12. So I keep everything the same. Now my next step is to get x by itself. So I would divide by 4. Now I'm dividing by a +4 here, which is fine. There's no issues with dividing by positive. It's only if we divide by a negative or multiply by a negative. So this is my answer. Okay, and then I'm also going to graph it. I want to be bigger than 3, so I'm going to go this way. And I'm using a closed circle. And you can always check, make sure you shaded the right side. So if I check here, let's say I test 4, if I plug in for x, is 4 greater than or equal to 3? It is. All right, let's try a couple more. Now here I have a fraction, but that's okay. So how would you cancel a fraction? I could cancel it by multiplying. So if I multiply by 3 on both sides, that would cancel it out, right, using that common denominator. So I'm left with just 1x is less than 15. There's nothing wrong with multiplying by a positive. Now 1x is just x, so my answer here is x is less than 15. And then, let's see, I need to be around 15, so we'll do 15, 14, 13. And when I read this, it says x is less than 15. So I want to be less than 15. I'm going this way. And I'm using an open circle here because there's no equal sign. And again, just give it a quick check. Pick a number to plug in. Is 13 less than 15? It is. So we know we graphed the right direction. Now here, I'm ready to solve. And notice that I have to divide by a -3 here. And because I'm dividing by that negative, I need to flip my sign. So the solving still works out the same way. I still get x. 21 divided by -3 is -7. But this sign here has to get flipped. So it's going to become a greater than. Be careful of your number lines. Remember, negatives get smaller down on the left. I want this to say x is greater than -7, so I'm going greater than -7. And again, if you're not sure, just test. Is -5 greater than -7? Yes, it is.